So normally at this time at the Zen Center, there's silence, and I can't compete with that, but we'll talk about the universe anyway. So the idea behind this talk actually came up, well, really about 20 years ago, but I'll share that story later. This is really from about 2 years ago. And the beginning of 2016, there was an announcement that a collaboration called LIGO detected gravitational waves for the first time. And I was super excited because I have a little connection with this collaboration. And I ran into Sunim a day or two later and was so excited and accosted him with all of this excitement about this new detection. And as I was talking to more and more people who don't have a science background, there was a lack of understanding of how profound this detection was. And so the idea for this series of talks really came out of a desire to put some context into these big things that we sometimes hear about in the news, big detections or big discoveries or theorems. Because without context, science can sound like magic. And without the proper context, it can be easy to disregard, and it can be easy to mystify or make it into something it's not. So we're sort of grounding ourselves. But at the same time, I chose this picture as the first slide because with the deep clarity of the natural world that you can find through science, you can see something deep within yourself connected to this universe or this planet or something much bigger than yourself. A technical word for this phenomenon in more recent times was called the overview effect. And it was something that happened when the first humans left our planet and saw it from outside of it. Something that they noted in astronauts when they came back to Earth was really a transformation of perception, that we really live on a planet that is just thinly protected with a thin blue line you can barely make out here in this image. All of life, everything we know and have ever experienced in this tiny planet. And so I hope to give some sense of that through a series of sort of talks that go a little bit deeper and deeper and deeper into the dirty details of some of the interesting things in cosmology and astrophysics. And I wanted to start with some words by Albert Einstein, because so many people think of him when they think of cosmology and astrophysics. This was in a letter that he wrote to a father who just lost his son. And there's different variations of this I've seen on social media, sort of edited to fit whoever is sharing the quote. But this was the piece of quote I found most interesting. A human being is part of a whole called by us universe, a part limited in time and space. He experiences himself, his thoughts and feelings as something separate from the rest, a kind of optical delusion of his consciousness. The striving to free oneself from this delusion is the one issue of true religion. Not to nourish the delusion, but to try to overcome it is the way to reach the attainable measure of peace of mind. So I don't know if we'll achieve that in the next 4 talks, but that's what we're going for. And so what I'm going to ask you to do is to think like a physicist for the next 4 weeks. And what I mean by that is something I'm calling the paradox of knowledge. I don't know if anybody else uses this term, but what I've come to realize in studying things that are quite complicated is the more knowledge you have about something, the more you realize you don't know. And this is different than not really understanding and also not knowing other stuff. That's different. It's not a paradox. But the paradox of knowledge is the more you know, the more you realize you don't know. And so to think like a physicist means to acquire the information and the understanding that you can, and at the same time be open to the fact that you will continue to move to a deeper and deeper state of not knowing. And whenever I hear Sunim mention only don't know from his teacher, it reminds me very much of this concept. And so today we're going to focus on what I'm calling the cosmological lineage. That these ideas are not just abstract, something completely disconnected from our human experience, that there is a tradition of passing information from one generation to the next, so that each discovery that we have today, or each realization we have today, has foundation, sometimes thousands of years. And so I'm going to break it into basically three parts: the ancient insights to cosmology. And by cosmology, I just mean our understanding of the universe. What I'm calling a pre-modern time, which was a shift of perception into what is modern cosmology, and something some of us are a bit more familiar with. And through each one of these, our perception of how the cosmos is will change, just like our ancestors. So this lineage is the birthright of every person. No matter where you come from, your ancestors had some concept of cosmology, to whatever level and to whatever orientation they felt. But before we move into the details, I want to warn you about something called the Trimble effect. And this is named after a professor at UC Irvine. And there was a recent article about her in Wired magazine, and it was titled "The Woman Who Knows Everything About the Universe." And I would amend it just slightly to say "The Woman Who Knows Everything That Human Beings Know About the Universe." Because her job for about 16 years was to read every single publication in astronomy and astrophysics and synthesize it for the community. So if you can imagine, especially as publications became digital, she continued and read everything, synthesized it, and gave it as a service to the field. And it actually fed into new directions of research, because she could not just see the dirty details of every individual project, but had an understanding of how they came together. And in addition to that, she is a noted historian of the field. So she doesn't just know the science, but also the stories of the people behind the science. And what she often points out is that when something is named after somebody, or someone is credited of being the first to do something or first to realize something, it's very, very rare that that person or that culture was actually the first to do it. So I'm going to talk about cultures and people who may or may not have done things, but take it with a grain of salt. What's more important is that there is a lineage of knowledge coming through humanity to what we're doing today. And as a side note, there's an episode of The Twilight Zone called Princess Twilight, which is a 19-year-old Virginia Trimble in black and white. And if you ever find it, send it to me, because I really want to see it.
So let's talk about ancient cosmology. So when I use the word cosmology here, it comes from the Greek word cosmos, which implies a universe that's fully connected. Today, in modern times, we often use the word cosmology to think of the context of the universe, so how the universe outside of this earth has expanded and evolved. But it is a bit more holistic than that. The term cosmos really implies that there is a connection with what we are to what's out there. There are 6 different concepts that I'll talk about here, which all of our ancestors had some concept of. And this understanding carried through time. So there are some ways that we celebrate and move through the year in particular that acknowledges these different concepts. So we'll talk about certain numbers, particularly number 7 in this talk: the equinoxes, solstices, the zodiac, retrogrades, and eclipses. And I'll just give you a summary of what these words mean astronomically, and then give a couple of examples of some of the ways these concepts from astronomy affected and inspired our ancestors, and even became sort of the foundation of our lives. So for example, number 7. Why do we have 7 days of the week, for example? These names in particular that we use, when you look back through the Latin at least, are named after these 7 objects. So we have the sun and moon, of course, and then we have 5 planets that we can observe with the naked eye. And all of our ancestors had some concept of the fact that these 5 bodies were not background stars. They behaved differently. And so there became a special divinity attached not only to these 5 objects, but combination with the sun and the moon to have a deeper meaning for our ancestors. And so you can see numbers like this in addition to 7. For example, why are there 12 hours in a clock? Why are there 360 degrees in a circle, when a circle can be divided into any arbitrary number of things? So even at the foundation of mathematics, the astronomical meaning became embedded into how we even view numbers. So these numbers that we've chosen as sort of base units could have been something different. But because, for example, there's 12 months in a year, things like that become special. So this is Mercury, Venus, Mars, Jupiter, and Saturn. These are the 5 planets that we can see. Mercury and Venus in particular had a little additional inspiration because these 2 bodies tend to disappear for periods of time because they're close to the sun and they go behind the sun. And they are only seen next to the sun. So that gives them a special place in this pantheon of knowledge. And so when we have certain numbers that show up again and again with regard to our daily life even, just know that these numbers didn't appear out of nowhere and often have some sort of natural connection, often astronomical. Some things are connected more with what's happening on the earth, but the best keeper of time was the night sky. And just a reminder what these bodies are. So the bright orange thing with dots, of course, is the sun, the moon next to it, Mercury, Venus, Mars. You can recognize here it has some polar ice caps on the southern side, Jupiter here, and of course, Saturn. So we can see this in some of our ancient ancestors by simple things like how they built their societies. This is Mesopotamia. Over 6,000 years ago, they were not only understanding the concept, but already building massive structures that indicated they understood how important these numbers were. So these observatories, these ziggurats, had 7 different terraces on them, indicating one of these 7 bodies. And this one on the right is a romantic version of what the Tower of Babel must have looked like. But again, you can see the 7 layers connected with these 7 precious bodies. And the one on the left is more of an exact drawing from ruins in the desert of Iraq. So one of the ways we can conceptualize our ancestors' understanding the sky is a way that's actually still useful today. And it's called a celestial sphere. So if you imagine the dome of the sky extends out and around the entire Earth as a sphere. So a plastic, if you will, ball has a northern celestial pole and a southern celestial pole that extend over the Earth's north and south. The equator of the Earth extends out along this disk here to the celestial equator. And on the background of all of this, the stars are painted, and the stars don't move. The apparent motion of the sky comes from the rotating Earth within. But the background stars are fixed and unmoving, so a concept of a static universe. But this line here indicates the path that the sun takes through a year. It's called an ecliptic. And it's an imaginary line, and the sun moves once a year around it. And on June 21st, the sun is at the northernmost point along the ecliptic, so the closest to the North Pole. And it's at what we call the Tropic of Cancer. So on a globe, you often see the Tropic of Cancer written. And what that is just a projection of this northernmost spot onto the globe from the celestial sphere. So it has nothing to do with what's happening on the Earth. It's simply an alignment of the sun. 6 months later, the sun moves to its southernmost point, and it's called the Tropic of Capricorn. Likewise, that line on the globe in the southern part is projected from the some winter solstice. So the northern and most southern points are what we call the solstice. And then this point here, where the path of the sun intersects with the celestial equator are what we call the equinoxes. The vernal equinox on one side and the autumnal equinox on the other. So these points were well known by our ancestors because not of what they could imagine in the sphere, but because of what was happening on Earth in response to the shadows cast by the sun at these certain points. And along this line, this ecliptic, you can see that the sun passes through certain stars that are painted on this celestial sphere. And these stars have forms. When we look at them, our brain creates forms out of the spots of the stars. And these constellations that we've created lie along the ecliptic. And these stars became special for that reason. We look at this picture to get an idea of what we may be seeing from the Earth itself. So this is an image from the southern hemisphere, the Anglo-Australian Observatory. And this point in the center is the celestial South Pole. And these tracks are what you see if you were to leave a camera open through the night, that the tracks follow and rotate around the southern pole. Likewise, the North Pole, the Polaris, has the same kind of tracks if you watch it through a night. So if we look at a person standing in the northern hemisphere, what do we see from this celestial sphere projected down to the Earth? So these yellow lines indicate the path of the sun. So for example, June 21st, the summer solstice, the northernmost path, the sun rises in the east, sets in the west along this yellow line. And we can see the extended daylight compared to, say, these other times. So March and September, rising and setting along the center line, and the southernmost point, the winter solstice, again, rising in the east and setting in the west. So you can see here, just by the size of the lines, that the summer solstice day is much longer than the winter solstice. And we know this by living here on Earth our whole lives. It's nothing new. But this was well understood by our ancestors. And this was extremely important for reasons of understanding the seasons, when to harvest, and either this most interesting concept of divinity. So if you imagine the sun is like a deity, it moves down from high to closer and closer to the horizon as we get closer to winter. So this might be a cause of concern for the people. And so you'll see that our festivals of light in the northern hemisphere generally revolve around time close to the winter solstice. And this was not just to sort of celebrate the darkness. It was really a calling back of the source of light. Because after the winter solstice, if we're fortunate, the sun would rise, the warmth would come back, and it would be an easier time to live. And so those in power utilized this knowledge of the rhythms of the year to sort of control and inspire people how to behave at certain times of the year. So if you don't call the sun back at this time and do the required rituals, you may be out of luck. A more modern version of this drawing is here, taken in a photo in Japan. These yellow lines, the same kinds of yellow lines we saw on the last page. So the winter, summer solstice, and the equinoxes in the center. And so this kind of shape you will see anywhere in the planet if you take a picture of the sun at the same time every day for a year. And what's indicated here is the person kindly took a photo during one day, the path of the sun. And if you were to extend and take a photo every few minutes through the whole day, it would follow this yellow line. But then if you go every week or so at the same time, 7 a.m., and take a picture of the sun, this is the shape you get. It's called an analema. And the orientation and the shape of the analema has to do with the tilt of the Earth's axis and also the orbit of the Earth itself. And it's actually quite complicated to translate, but each planet in our solar system has a different shaped analema related to its orbit and also its axis, how it faces the sun. Ancient ancestors didn't have the technology to do this kind of Photoshop work. So what they did was watch the shadows. Literally, a stick in the ground can give you an indication of how the sun moves. But many of our ancient cities and structures were built in a way that helped give them a concept of really the precise position of the sun at different times of the year. So let's look at how they accomplished this understanding of the sun and translated it into architecture. So we look at India. The Rig Veda contains the first known of references to astronomy. Dates between, depending on who you ask, 6500 BCE or 4000 BCE, maybe even older. And some of the jewels in this source are, for example, references to the sun as the center of spheres. So a source of light, center of creation, but in particular referred to as the center of spheres. And so some argue that this means that they understood that the sun is the center of the solar system, a heliocentric model, which didn't come for thousands of years in Europe, for example. One sutra that I find particularly sweet is this one, Sarva Dishanam Shriyaha Shriya. There are suns in all directions, the night sky being full of them. So did they understand that the sun was actually a star and not something separate from it? So this is a really sweet and interesting concept to reflect upon. And the picture that I have here isn't related to the Rig Veda. It's much, much, much older. And these were large bodies built in the 1700s after a supernova was observed. And the Maharaji was so impressed, he built these amazing, beautiful structures. Mesopotamia, about the same time here as the Indians, a little bit more recent, had a strong concept of, for example, the rise of 12 particular constellations that marked certain events and seasons to give people an orientation throughout the year. They were also able to distinguish between the fixed stars and the planets. And this idea that a circle is divided into 360 degrees is a concept from Mesopotamia. And in fact, this degree symbol is a symbol of the sun, because the sun takes about 360 days to rotate through that celestial sphere. To the other side of the world, the Incan city of Nazca in the Pampa, Colorado, there's this extended plain with shapes and lines and all kinds of crazy things. It's a source for many conspiracy theories about aliens, which may or may not be true. But the research that's sort of most extensive has been from the 1980s on, with a group of different scientists working together to sort of get a holistic view of what these pathways may be. One thing is that some of them are just societal pathways for religious movement of people. A particular corner in the Northeast focuses on things like the sunrise and sunset in the planting season, winter and summer solstice, rising of the Pleiades, a celestial llama, to mark certain special moments in time. And some of these lines indicate just sources of water, so very practical applications. So the beginning and end of a lot of these lines is at a source of water. And these lines are so vast that you can even view them from space. Making a straight line over an extended distance is no easy feat. It requires precise alignment. And in those times before surveying equipment like we use today, the most precise equipment was the regular repeated cycles in the sky. So the best clock and best source of alignment that we had at the time. And the Incans used this for that. And then the Mayans. The Mayan calendar is one of the things they're famous for, although it predates the Mayans. And the most recent cycle ran from about 3000 BC to just a few years ago when it ended, and the world didn't end. So this is Chichen Itza, more recent than the Mayan calendar. But this building here is called the observatory, but really the whole city is an observatory. This pyramid in particular attracts people every equinox. So what happens is the sun at the equinox projects along the side of this pyramid against a wall like this going down the stairs. And at the base of the wall, there's a snake-like head indicating Quetzalcoatl, the serpent god. And as the light projects on the wall, it looks like a serpent slithering down the pyramid. The observatory itself has alignments particularly related to Venus, which was of importance, another symbol of the god Quetzalcoatl. But the entire city was built around the awareness of the position of the sun, position of Venus at different times. And the Polynesian astronomers really took this and applied it not just to building structures, but to moving around the ocean. So there wasn't a lot of land. And these arrows indicate the movements of people using a GPS just from the stars. So in order to do this, they didn't have just a concept of where things were in a static world, a static cosmos. They also had a profound understanding of how things changed with quite good precision in order to be able to make it and survive these extensive journeys in just simple boats.
Why did our ancestors focus so much on the night sky and trying to align it? Well, there's sort of spiritual reasons, like I mentioned. A lot of our deities and ideas of faith came from these objects in the sky. But a theme that we're going to see over and over again is there's a concept of time. So we can use things and events on the earth to measure time at the scale that they were looking at, how seasons change and things like that. But the night sky is an extremely accurate clock. And so this search for sort of nailing down and coming to precision on time really led some of these traditions. And additionally, just trying to find meaning. Why is it there? Why are we here? So part of the problem that began to arise, so we figured out, the humans figured out sort of when things happen in cycles, but as they began to think a little more and wonder a little more, the problems began to arise and began to float to the surface. And one of them was the problem of the planets. So back to this image of this, ecliptic, sorry. We have the path of the sun denoted here. But there's more than the sun that runs along this line. So these are the wanderers. The Greeks really obsessed about this. This object here indicates Mars. So generally the planets follow the same line as the sun across the sky. But every once in a while, they'll sort of misbehave and sort of come off. Each night, if you take a picture, it moves a little bit off the ecliptic, and eventually it even starts moving in the wrong direction. This is what we call retrograde. In astrology, that seems pretty meaningful. I'm not sure why, but the planet seems to go backwards. And then it slows down and stops and then continues on and eventually behaves itself again. So this was like a little problem that when you have enough precision of what's happening, it becomes very clear. Something is not right. And so this question of what's happening, why is this not right? Why doesn't it fit my model of how it should be? Was really the food for cosmology going forward. Another very important object on this celestial sphere, this yellow line is the sun, and this white line is, of course, the moon. Pretty important and significant object in the sky. So the sun moves around this sphere once a year. The moon moves around, any guess? Once a month. Okay. So the speed of the moon on this path is different than the speed of the sun. And these two paths are about 11 degrees off. The two paths intersect, and we call these nodes where they intersect. And because of the orbits of these two bodies, these nodes actually precess with time, which means that the nodes spin around this collective cycle. So the place where these two lines intersect must have been quite startling for people watching the sky, because if you perceive the sky to be a sphere, like we do, The sun and the moon run into each other at this point. And if these are your deities, that can be problematic. So this becomes a little more complicated. So up to now, it was pretty easy to understand a lot of things with the celestial sphere concept, which carried us quite far. But when we start looking at the moon and the sun, since we know there are three things involved, it's something called a three-body problem, which is only for the mathematics people. But it means that it's very messy to figure out how three things are pulling on each other with gravity. But our ancestors didn't know about the math. They didn't know it was complicated. They watched for extended periods of time and mapped the cycles over and over and over and over and over for hundreds of years to get a concept of how these nodes were behaving. Because what's happening on these nodes are what we call eclipses. And we have to step out of the celestial sphere model to look at what these are. So just a reminder for those of you who know what these are. A solar eclipse is actually when the moon finds itself between the Earth and the sun. And the moon casts a shadow on the Earth. So the very dark part of this shadow is what we call a total solar eclipse. And this sort of lighter part, which is a partial shadow, is the partial solar eclipse. So solar eclipses happen actually quite often, a couple times a year generally. But the problem is that they're very local. So if you were an ancient astronomer who happened to have caught an eclipse in your lifetime, and your job was to figure out when it was going to happen again, you would likely fail because it wouldn't happen again in your lifetime. There are some astronomers who lost their head because of this very problem. So solar eclipses are very rare. Has anybody seen a full solar eclipse here? So a couple people. It's not that common. And then we look at lunar eclipses, which is the opposite. So this is now, the moon is on the other side of the Earth, and the shadow of the Earth is covering the moon. And again, they happen about twice a year, these nodes that are on the two paths of the sun and moon. But it's a non-local event, which means that about half the Earth can see some part of the lunar eclipse. So the cycle of these eclipses at any particular point on the Earth are a little more regular and a little easier to predict. So the job of the astronomers was a little safer when predicting lunar eclipses. But this is the power of extended practice. The Chinese, for example, and Koreans, I was looking up in this, were able to predict some of the solar eclipses only about 2,000 years ago. But they used a cycle of 135 years. So they had to have studied the sky multiple times, hundreds and hundreds of years, to figure this out. It was actually about 2,000 years of data it took to be able to predict. And then shortly after that, only a couple hundred years later, they were able to actually really properly figure out the positions of the three bodies, the Earth, Moon, and Sun. The Mesopotamia, similarly, could also predict some lunar eclipses. And about 2,000 years ago or so, they could also figure out these three bodies. Again, it took thousands of years of data. And some of this data is what we have as the foundation of what we know now. There might be indications the Egyptians and Mayans knew also a bit more about eclipses than what we realize. But much of their documentation and knowledge was lost in fires, either from the invasion in the case of the Mayans or the Library of Alexandria burning and destroying much of the Egyptian knowledge. So to give you a sense of what these cycles look like, this is a more modern version of something like what our ancestors did. So each of these vertical lines is 18 years. So this is extended years. These golden circles are total eclipses. These black circles are different partial eclipses. And you can see just a pattern emerging. And even at this scale, there's not an exact pattern. So these movements are so complicated that finding an exact pattern is very hard. But there was a close approximation of about 135 years, at least for solar eclipses. But if this is too much and too heady, this is a local phenomenon. We still live on the Earth. This is not theoretical. This was in Wenzenbach, here north of Regensburg, on July taken with an iPhone through a really cheap telescope eyepiece. And 11:30 at night on July 27th, when most people had gone to bed, there was this dark moon in the sky, and all of a sudden this brilliant light emerged from the side of the moon. And it was just the moonlight in a dark sky. But if you watch through a really simple telescope, you could see the Earth moving out, or the moon moving out of the Earth's shadow. And you could even see the craters on the moon revealing themselves at the light. So although like some of the ideas that we're going to talk about are sometimes heady or sometimes heavy to think about, go outside and look up and see what's there. So we're going to transition to what's I'm calling pre-modern cosmology. So this is still a little bit in ancient times, but there's going to be two cultures in particular I'll mention before we get into sort of some more familiar names. And again, watch for this Trimble effect. So I'm going to talk about different cultures and different people who did something, who may or may not have been the person who first did it. But the lineage is stronger than each individual person who contributed to it. So the knowledge that was valuable was passed on, and the knowledge that was not was lost. And I can't say that all valuable knowledge was passed on, but at least some of it was. And this is how. So we go back to the Indian tradition. And around 500 BC, Aryabhata, a very famous astronomer and mathematician at the time, presented his text, which is a treatise on the state of knowledge of mathematics and astronomy at the time with some corrections. And he had just a few I'm going to mention here. The glow of the moon is reflected sunlight, which we sort of take as a given, maybe. But this was not really known by a lot of other cultures at the time. The motion of the heavens, he proclaimed, was due to the rotation of the earth, but even in his time life, his contemporaries didn't really accept this and often just sort of left that part out. Lunar eclipses, he predicted, was the shadow of the earth as opposed to a demon covering the moon. And he was able to estimate the length of a year to within about 12 minutes of what we estimate today. So again, this was not one person alone, most likely, but a codification of a tradition of knowledge about the sky and about mathematics. And it wasn't until the 13th century, when this was translated to Latin, that Europeans picked up some of this knowledge and integrated it into what they were already working with, particularly some mathematics, calculations of triangles, volumes of cubes, as well as the square and the cube roots. So these are mathematical traditions. And what really sort of makes the transition from ancient to pre-modern are two things. This concept of time gets a little more precise. And mathematics clearly becomes dominant in our understanding of the natural world. So it's not just creating tables and looking at things, it becomes more complicated. And of course the Greeks, so there's a strong Greek connection here. And if there are any Greeks in the room, they are often raising their hand saying, no, but the Greeks did it. So they did. They did a lot of stuff. I'm going to mention a couple of them here. So 500 BC, the Earth was a sphere and measured, so influenced by Pythagoreans. About 100 years later or so, we had Plato looking at the problem of the planets. And this is another thing that indicates this is moving already into the pre-modern age. So the Greeks had an image of the cosmos, and the cosmos was the natural order of the heavens. And the cosmos was connected very much with this life force, this human experience of nature and reality. And spheres, I'm not sure how they got it stuck in their head, spheres were the representation of that perfection. And the planets violated this perfection. And so it really became a problem. This is the foundation of sort of astrology as a personal astrology. So many cultures have some concept of astrology, but not quite as personal as the astrology that came out of this concept, where astrology now corresponds with something in the heaven corresponding to something in this body or in this life. The Greeks also came up with the heliocentric model much, much earlier than the European culture where sort of modern cosmology came out of. Aristarchus of Samos and Archimedes are credited with the first understanding of the heliocentric model, but the Chinese might disagree with that. And then Aristotle, he followed this humanistic approach, so this cosmos approach, really to extremes, really disagreeing with sort of what the astronomers or the studiers were finding by looking at the Earth and taking measurements. If it conflicted to how we perceived reality, it was negated, at least in Aristotle's teachings. But he did have some interesting thoughts on time, which Einstein sort of brought to fruition quite a bit later. So the written language of mathematics. So I mentioned this Aryabhata from India. So 1220, there was a guy named Leonardo Pisano Bigolo from Pisa. In the 1800s, his name was mistranslated as Fibonacci because the translator wrote his name as the son of Bonacci, Fibonacci. His name was not Fibonacci, but now the name Fibonacci is the one that people recognize. So I'm going to call him Fibonacci from here. He helped bring the teachings of Aryabhata and the Indians and the Arabic mathematicians into Europe by translating it into Latin, their teachings. One of the most valuable things that his writings did was bring our written system of numbers that we use today. Because the system of numbers used previous to that were very complicated to do any kind of calculations. So we found a way to write numbers, to write mathematics more elegantly and to work with it. And the other thing he did was introduce a riddle about rabbits. This is not his riddle, but he's credited with it. It was actually about 1,000 years earlier. Riddle is quiz auf Deutsch. Rätsel, thank you. It's a Rätsel. So this is what he posed. If we have a pair of rabbits, and after 1 month, the pair of rabbits mature and mate, and after 1 month, they have their first babies. How many rabbits will you have after a period of time? So each rabbit pair needs a month to grow before they can mate, and after they mate, they need another month to produce a pair of babies. And the answer for how many generations of rabbits are there each month is a sequence of numbers. So you have one, the first generation, again, one pair, the second generation, next generation, 2 pairs, 3 pairs, 5, and so on, 8, 13. What you see in this sequence is the third number is the sum of the first 2. The third number is the sum of the 2 before it, and so on. And this is a simple sequence of numbers that has some profound implications when you want to look at patterns in nature. And it basically shows you how nature grows. So these are some examples of Fibonacci spirals. And what this is if you take a box of a size 1 by 1, 1 by 1, 2 by 2, 3 by 3, 5 by 5, 8 by 8, 13 by 13, 21 by 21. If you take these boxes and you fit the boxes from diagonals with an arch, and you add these boxes together, you will reproduce a spiral that is found in nature from the very large to the very small. And it's found all over. This is Jupiter, and these are storms on the surface of Jupiter. This is a storm on the surface of the Earth. A spiral galaxy, some plants, snail shells. So everybody has seen these spirals. The Greeks had a similar spiral, the golden spiral. This is an approximation of the golden spiral of the Greeks, but it's a similar spiral, and it shows how nature grows. And I don't have a big punchline for this because we don't know why. This is how nature grows, and we don't know why. There were some thoughts that perhaps this orientation is just an efficient way for things to grow. That may or may not be true, but nobody's really figured out how. Some researchers recently, for example, looked at how plants distribute their leaves and branches finding the spiral again. And they assumed that this distribution had something to do with the efficiency of collecting light or water or something. But there are actually other configurations that can do that better. So this is how nature grows. And Fibonacci is credited with this sequence, although it's actually much older than him. So for thousands of years, people have had a sense of how nature grows. What it means, we don't know. And then as we move on through time, so we sort of skipped about 1,000 years in there. So we're going to move on to some names that are a little more well-known, and looking at things like data and math, which don't sound very, very interesting, but they're the foundation of what we know today. So Nicholas Copernicus is credited with the heliocentric model, which he reluctantly shared in Europe, again, about 1,000 years after the Greeks had come up with the same idea. He was really reluctant to share it. He sort of created writings and gave them out to his friends. And then one of his friends outed him at the church that his teachings were there, because he was afraid of the criticism and didn't know what the feedback would be. But the church at the time actually encouraged him to publish. And there's a romantic story that on his deathbed, his publication finally came and he saw it, but not sure how true that is. At the time of Copernicus, there was an observer named Tycho Brahe. If you want to look up interesting theories about weird astronomers, he's the one to look up. A lot of stories about him. He was still fighting for the Earth-centered view, but what he did is he took observations of the Mesopotamians and he extended them, and he became an extremely good observer, collecting extremely precise data, challenged by the concept of time, because this is the time when we were trying to figure out how to measure small bits of time. So we can measure seasons, knowing when to harvest, things like that, but we couldn't measure more precise time in an accurate way. So this was when the concept of the second was being evolved in Europe. And one of the contributions that Brahe made in addition to his data was to develop clocks, because he didn't have a clock that was precise enough or consistent enough to do the observations that he wanted to do. And one of his students, actually his last student, was Johannes Kepler. And he has a particular connection with Regensburg because he died here. So if you go to Keplerstrasse, there's a really nice museum with pieces of astronomical instruments. And he did actually quite a lot of work and contributed significantly. He was also a thief, because as the student of Tycho Brahe, he was not allowed to have his data. In his lifetime, Tycho Brahe would not give his data to anybody, including his student. So after he died, Kepler stole it. And his work on the 3 laws of motion, so he figured out that not only are the planets orbiting around the sun, their orbits are defined by an eclipse. So he wasn't as interested in making observations as taking the language of mathematics and making sense of the observations. He wanted to be able to predict what's happening and explain why. He didn't really get to explaining why, but he could predict the motions of the planets. And his work was based on observations of Mars in particular. But later, contemporaries were able to apply his method and look at the orbits of other planets. He also designed the astronomical telescope so that we could start looking into the sky with more than our eyes. And as an aside, he wrote possibly the first science fiction book about a witch and got his mom arrested, witches were, his book apparently was so good, they thought it must be based on his life. His mom got arrested. So Galileo Galilei. So these are names that some people have sort of heard of, so I'm going to go with these. Remember that they were not alone, and they did not work in isolation. In fact, Galileo and Kepler collaborated. They knew each other. Galileo used the telescope that Kepler designed to look at the stars and planets, and found not only are we orbiting a sun, there are actually planets out there with moons orbiting them as well. And a lot of things that are not stars exist in the sky. And this became the root of sort of the problem that pushed people forward from there. He also began to examine what would later be called gravity, figuring out how things fall. And again, his problem with a clock was the same as Kepler's. How do you measure how quickly things move if you can't have a precise measure of how long it takes to go from here to there? And he came up with a quite useful solution. Does anybody have an idea of what moves or what ticks at 1 second per second? 60 times in a minute? Your heart, yeah. He used his heartbeat to measure time, which is not very accurate, but if you're resting, you could use it. If you're dropping balls from a tower, your heart rate might be a little high. So, but he used that as a close approximation. And then time enters into the equations literally at the time of Isaac Newton. Or Leibniz, we're in Germany, so I have to mention Leibniz as well. So Leibniz and Isaac Newton are credited with developing what became known as calculus, what became a language of mathematics that includes time. Although time is sort of a passive player in this language, what becomes clear here is that language of nature is mathematics. And so the story of cosmology and astrophysics and astronomy can't be told separately from it, because as our clarity about what's happening evolves, we need a way to communicate it and to express it. And clearly the language of mathematics is the way. So what Newton did in the late 1600s is develop what were called the 3 laws of motion. And he introduced this word gravity. So this idea that everything with mass is pulling on everything else with mass. So it's not just about what we see in the sky, it's about interactions here on Earth. And as we move forward, it's not that astronomy is some esoteric thing out in the universe. It's connected with the very materiality of our every moment in everyday life. And if we can understand the very, very small, it gives us a concept of the very, very large, and vice versa. So the 1800s, we're slowly marching up to about 1905, and we're going to stop at 1905 for today. So the 1800s, there were some revolutions in mathematics, astronomy, computer science, and engineering that became the foundation and kind of the problems that became the transition into what I'm calling modern astronomy. So we have James Clerk Maxwell, and I'm putting et al. Next to it, which means there were other people working on similar things and developing. So this picture I included here is somebody's arm in Regensburg. I don't know who he is, but I saw him on a bus, and I had to walk up to him and say, "You have Maxwell's equations on your arm." And he was very proud, so he let me take a picture. So I'm guessing a physics student in Regensburg somewhere has Maxwell's equations on his arm. So if you're looking, for another tattoo, I can recommend. It's pretty cool. Astronomy. So Caroline Herschel et al. And a bunch of other people started looking at the night sky with telescopes that were getting better and better and better with time. And we discovered that there's a lot of stuff out there that are not planets or the sun or the moon. In fact, most of the universe is fuzzy stuff out there. And so they began to catalog and catalog and catalog. Messier is a very famous one as well, who was about 100 years earlier. They were able to find there are actually other planets in our solar system orbiting the sun that we can't see with our eye. Her brother William Herschel is credited with finding Uranus, for example. So we began cataloging and cataloging more detailed stuff like the ancestors, but now on a much more fine level. Computer science, Ada Lovelace and her contemporaries were credited with developing the first computer program. Program. So she wanted to essentially synthesize a brain, what a brain does. And she was able to do that using binary mathematics, which is sort of an esoteric concept of mathematics at this point. Because you turn something on, you turn something off. Like, how does that contribute to intelligence or information? And this is the foundation of what we use today, things like this, on, off, on, off. And it is really the heart of what I'm calling lineage here. Just one piece of information transmitted and shuts off, and one piece of information transmitted, shuts off. This is computer science, and this was fundamental in sort of the transformations coming 200 years later. And then there's Nikola Tesla and Thomas Edison, who took this theoretical understanding of what we now call the electromagnetic spectrum, so the wave nature of light is what these equations talk about. I won't have many equations in this talk, but this was too good not to share. So these equations tell us that light moves as a wave, and it tells you how it moves and how it's related to magnetism. And what Nikola Tesla and Thomas Edison did was they took this theoretical knowledge and transmitted it into utility, electricity. So Tesla invented the alternating current that we use today. Edison was the master of utility. He's credited with many, many things which he didn't do, but he hired the people who did it. For example, Lewis Latimer is the one who invented the light bulb. He was the one who figured out how to make a light bulb that lasted more than a burst of light using tungsten as the filler inside of it. So this was sort of the transition from kind of pre-modern sort of mathematics coming to life to really applying the mathematics, looking out further into space, and then utilizing obscure kinds of mathematics which seem to be separate from reality, and realizing that there's some kind of practical application even for the most outrageous math. So we move into modern cosmology. I use this term because in 2000 I was part of a summer school on the history of modern cosmology. And basically it was from 1905 up. So we're going to move into modern cosmology. Just to give you a taste of where our modern understanding of things like quantum physics, things like thermodynamics, things like relativity, where these came from. And basically they came from one source. There were other people working on it, but these 4 papers published in 1905 essentially became the foundation of our understanding of reality from that moment forward. So these 4 papers were published by Albert Einstein. And there's sort of, I don't know how it is in Germany, but in the US, there's kind of this mythology around Albert Einstein. Like he was really bad at math and he was a terrible student, which may have all been true. I would argue he was not very bad at math, but he was quite unhappy with the mathematics education system in Germany, and so he left. But he didn't drop out, and he didn't sit and just think about things not connected with what was happening before. He was very cognizant of the developments in physics at that time, and he was very cognizant of the problems that existed at that time. So as we come in to what he's looking at, there were some problems. For example, there's what's called the Bentley's paradox, actually, Newton's paradox. And it means that if gravity works the way that Newton proposed, and that his laws and his mathematics were able to predict motion very well, very, very well. We could use his equations to do just about everything we needed. But there were a couple problems. One of them was that if gravity is pulling everything towards itself, how is the universe not collapsed? Because when we looked out at the sky, everything seemed to be really still, and nothing was collapsing in on itself. Through his equations, there's an implication that time is infinite. So time has always been and time will always be. And so one of his responses was that the universe is infinite. So with an infinite universe, everything can pull on everything and it hangs in balance. But people noticed when they looked out into the universe with these nice new telescopes we had that there was clumpy parts. So it wasn't all homogeneous. It wasn't all spread out. So how is it that everything stayed balanced? And when that conflict arose, this is a little bit the Aristotelian thinking again, that when the conflict arose with my perception of reality and what the mathematics and the science was telling us, you have to make a choice. Either you go with what you're seeing or you go with what you believe you should be seeing. And Newton went a little bit with what he believed he should be seeing. And the hand of God was what fixed that little problem, at least up until this point. And then there was a problem with Mercury. So the planets' orbits were a well-established problem. They could figure out where planets were going to be. Newton's equations explained why and how, but Mercury didn't behave quite the same as the other ones. And there was a little problem with the orbit of Mercury. It wouldn't quite stay in the same way as the other ones. And so they couldn't predict its orbit precisely. And then there was a little problem with light. So these Maxwell's equations that worked so well at creating the foundation of electricity, magnetism, utilization, so creating current, having people use electricity in their daily life, but it didn't work when things were moving. And there were some other small problems, but sort of really important problems in the existing structure. And so these are the problems that he addressed in these 4 papers. They didn't just come out of the blue, they came out of these existing questions that were going unanswered. So I'm going to go through just the 4 of them to bring this to close. So the first one, I'm going to leave the English here. I almost put the German, but then, so this is the English version. On a heuristic point of view about the creation and conversion of light. And this is actually what he won the Nobel Prize for. It had nothing to do with gravity or general relativity. It had to do with the photoelectric effect. So basically, what he said in this paper is light is also a particle, and so are electrons. A movement of electrons is what we call electricity. So this is the wave theory versus the quantum theory of light. So the time average is what we call wave theory. This is Maxwell's equation. And then there's this quantum theory. And this is, for example, how your digital camera works, things that you use every day. What they saw at this time was that certain metals, if you shone light on them, a current would come out. A current is just moving electrons. So light would create electrons. But the problem was, if you would just shine more light on the metal, more electrons wouldn't come out. And this was quite confusing. And what he found in this paper was that only certain colors of light affected the metals and created electrons. If you were to put, for example, this red light here, no electrons would be produced. This has to do with quantum physics, which we'll talk about in a couple of weeks. I'm not going to go into quantum physics too much today. But this is the foundation of what would become quantum mechanics. And he was not so clear on quantum mechanics for the rest of his life. He argued quite a bit with the people who were looking to fully develop the theory because it made no sense. And it still makes no sense, just to be clear. Quantum physics makes no sense. But he didn't believe it could be that way. It had to make sense. It seemed too random. But his work was the foundation of that randomness that he didn't understand to the day he died. His second paper was the investigations on the theory of Brownian motion. So Brownian motion was something that was actually discovered about 100 years earlier by a biologist looking through a microscope. And if you see a little fleck sitting, a little dot of something, a tea leaf, let's call it a tea leaf, floating in water, the tea leaf will move. And it will move in this sort of crazy way we call a random walk. And so somebody who saw this one day decided we should try to figure out how this thing is moving and why. And they couldn't figure out, there was no sort of clear way to describe the movement of a flake of tea in hot water. And basically what this paper clarified is that atoms are a thing, and statistics, which is a field of mathematics that was sort of seen as not particularly useful to real-world applications, statistics too are quite important. And through this work, he was able to calculate the size of a molecule. And this paper became the foundation of what's called thermodynamics, the kinetic theory of heat. And it's using statistics to explain macroscopic events like this one. So basically, this tea leaf moves because these atoms or these molecules of water are bumping into it. And they're bumping into it in such quantities that they can actually move something much larger than themselves. So again, this is the second field of physics which essentially arose out of this insight. And so you notice these insights aren't huge. It's just a little shift in how we perceive things and what might be. And then we get to the weird stuff. So the third paper on the electrodynamics of a moving body. So basically what he said here is physics is relative. So there's this concept that the laws of physics are the same no matter where we are. And there was a little shift, which he said the laws of physics are the same no matter where you are, but how I perceive my little space and your little space is not necessarily the same, particularly when we're moving. And what he proposed with the speed of light is a fixed quantity. So for example, if you're, I'll tell this was an inspiration for my summer vacation. I come from Phoenix, Arizona. And in Phoenix, where my parents live, you'll see mailboxes that are fortified. They have like bricks around them. Because sometimes young people, when they're bored, will take a baseball bat while in a car and hit mailboxes and destroy them. And if somebody has gotten their mailbox destroyed a few times, apparently they fortify them in Phoenix, Arizona. So it's got me thinking about how to explain this. So if you hit a mailbox with a baseball bat, you might dent it. But if you're in a car and you hit a mailbox with a baseball bat, the mailbox flies, and it's kind of funny to some drunk teenagers in a car, I guess. So your speed of hitting the mailbox with your bat gets increased because you're in a car that's moving fast. That's how velocity, speed usually works. But if you have a flashlight and you shine it on a mailbox, the speed of light hitting that mailbox will be the speed of light. If you're in a car and you turn on a flashlight on a mailbox, the speed of light hitting that mailbox is the speed of light. So you add the speed of the car to the light and you still get the speed of light. So you add something to something and you get the same result, which doesn't make much sense. I'll explain it this way. So this is my friend Dieter Forster. He's a professor at Temple University, and he rides a bike. He's German, and he's the only person in Philadelphia who rides their bike to work every day. But I mentioned this series of talks, and he's a longtime mentor, so he had ideas, and I threatened to show a photo of him, so he gave me this photo to show. So if Dieter is on his bike, moving through space at some speed, he's also moving through time at some speed. So the normal speed of time, does anybody have an idea of sort of the normal speed of time? It's about a second per second. So every second, time goes on for a second, only in one direction. So one of the implications of Einstein's work in this paper were that there's a speed limit. Essentially, there's a budget you get of total speed, including the time speed and the space speed. And that's indicated by this black line here. But if we put Dieter on a rocket and send him through space, his speed through space increases. We have this same budget of total speed that he's allowed to have, which means that his speed through time has to decrease. So his speed through time decreases from our perspective. So time in my world, where I am, is moving at a second per second. Dieter's world, it's also moving at a second per second. But when I watch him on the rocket, it seems to me that his time is not moving at exactly the same way my time is moving. And so this is a subtle but profound concept called space-time. So before this, time was this thing that moved at a second per second for everybody in all places. What this implied is that time is now a thing that can contract and stretch, very much like space itself. So the term space-time means that now time is part of the material universe somehow. And this founded what eventually became what's called special relativity. Took another 10 years to become what's called general relativity. But for now, this is called special relativity. And this has all kinds of crazy, loopy results. So a lot of times we talk about time dilation. We were talking about a movie called Interstellar, which I can totally recommend. Interstellar had a fantastic science consultant named Kip Thorne. And he got the Nobel Prize last year, and for the gravitational wave discovery, which is sort of the impetus for this talk. So this movie called Interstellar goes into time dilation really beautifully, because one of the implications of this work is that if you're close to a source of very strong gravity, your perceived time by an outsider will be different. So some of the characters in the story lose time compared to their ancestors back on Earth because they get close to a black hole. So the physics in that movie is very good, just a heads up. Star Wars, not so much, but Interstellar is really, really good. So that's the third paper in this series. So the first paper was a foundation of quantum physics. The second paper, the foundation of thermodynamics and heat. The third paper, special relativity, which would blossom in 10 years once the math caught up into what's called general relativity. And the fourth one, I saw this and thought of the Zen Center. So E equals MC squared is not my coffee squared, but I think it's a good representation. And I'm pretty sure this is not a real photo. Just a little bit of fake news. So the inertia of a body, does it depend on its energy content? And what he found here is energy is related to the mass times light, the speed of light squared. So C is how we represent the speed of light as a constant. And what this was able to do was to unlock the power of the atom. So Lise Meitner and Otto Hahn, quite a while later, so about 30 years later, finally were able to use the information from this equation to predict how we could split the atom. So Lise Meitner did the theoretical work with her partners, and Otto Hahn did the experimental work in the lab. And it's a very interesting story. Lise Meitner was in Berlin. She was actually the first female professor of physics in Germany. Unfortunately, she was also Jewish in the late 1930s. And so her collaborators, including Otto Hahn and some from Northern Europe, smuggled her out of the country. In fact, Otto Hahn gave her an engagement ring, a family heirloom, to take to bribe the guards in case they couldn't get her across the border. And so she luckily made it out safely and reestablished her research program eventually in Stockholm is where she landed. And they continued to collaborate via letters. And so he would do the work in the laboratory, send her the results, and she would give the theoretical understanding. So she was the one who figured out sort of the last piece to unlocking nuclear fission. And in 1944, Otto Hahn won the Nobel Prize for it. And so this question of time comes back again. So what is this thing called time? Have you ever thought about it? Like, what is time? We can have a sense of like sort of what atoms are, you know, what this physical world is. But what is time? I don't have an answer for this, but think a little bit about this. Maybe the question in the next sitting practice. What is time? Is it a measurement? Is it an experience? We'll talk a little bit about the experience of time versus time itself in the third talk. But this concept of time is sort of what's bringing people forward in their search to understand cosmology in the universe. It began simply by understanding sort of day and night, seasons moving, when we plant things, when we harvest things, when we perform certain rituals. And we required it to be a bit more precise as we tried to really answer some of the unanswered questions. And in all of this time was a background player. So time was sort of assumed to be a fixed thing. And at the beginning of the 20th century, time was no longer fixed. Time was as free as anything else. And so this taps in a little bit to what it means to move through time, what it means to move through space. And we can use this as a source of contemplation. So this is a picture of a modern Earth. If you get the chance, find a place that's dark, like this. Has anybody ever been to one of these dark places? So the night sky looks nothing like what you think it looks like. The night sky of our ancestors cannot be seen in Europe, most parts of the US, East Asia, India. The night sky is completely different. So these concepts affect our everyday reality. They affect the technology that we use and take for granted. And we'll talk more about sort of how they build up from there. So this is just from ancient time to the beginning of the 20th century. And just like this growth that we saw in the Fibonacci sequence, everything grows sort of exponentially. Our knowledge exploded at this early 20th century mark. And we'll talk about the implications of that in the next week and the week after. And then in the fourth week, we're going to talk about the Nobel Prize from last year, the gravitational waves. This has a particularly special place in my heart because 20 years ago, I got to work for a short period of time in the collaboration. And Kip Thorne was my mentor. He was the one directing the program at the time. And in that space, I had went from a student sort of doing my studies every day in the classroom. You know, you do your studies, you do your grades, and you feel like, what's the point? And when I had the chance to work in this collaboration, I realized that I was part of a lineage of knowledge. Even just my little part of sort of, you know, figuring out my problem and presenting it. And so that each one of us has a part to play, even in this knowledge, even if it's sitting and contemplating in a dark space, the sky above. This is a famous poem by Sarah Williams. I encourage you to look up the entire poem because it's a beautiful way to express the beauty of lineage, of handing down knowledge from generation to generation. It's called The Old Astronomer. And one of the beautiful lines you see often used is, "I have loved the stars too fondly to be fearful of the night." And it's the story of a dying astronomer talking to her pupil just at the end and sharing what they've shared together and trusting that the student will take it and continue on from there. And so I'm going to leave this here and take a moment. And if there's any questions, I'm happy to answer.